Okay, it's my pleasure to introduce our next speaker, Paul Kinlaw from Austin University. We'll talk about progress towards the generalization of Mertens' theorem for almost primes.
Thank you. It's an honor to speak today at the Maine Quebec conference. And so this is joint work with Jonathan Bayless, who's in the audience, and Jared Lichtman. So Merten's second theorem gives an estimate for the sum of reciprocals of primes up to x. So we have double log x plus a constant plus an error term. So it's big O of 1 over log x. And here's the constant. So it's known now as Merten's constant. I don't think he called it that, but so it's known as now. And the prime number theorem gives a better error term. For instance, it's big O of 1 over any power of log x. So implied constant depends on the power. In 2014, Dumitru Papa proved a similar estimate, but it was a sum over primes p times q less than or equal to x for the reciprocal of p times q instead of just p. So it's the square of double log x plus b minus zeta of 2 plus an error term that, like the one in Merten's theorem, has limit 0 as x tends to infinity. The sum is overall ordered pairs PQ of primes whose product is less than or equal to x. And Papa's proof uses the hyperbola method. So we look at points in the first quadrant of the PQ plane that have prime coordinates and lie beneath the hyperbola PQ equals x. So let's let L be double log x for convenience. And this ominous condition sort of is a telltale sign of a number theory conference. And recall Papa's 2014 result. This is from the previous slide. In 2016, he proved a similar estimate for the sum of reciprocals of PQR over all ordered triples of primes PQ and R, whose product is less than or equal to x. So now we have double log x plus b cubed, and then some smaller order terms. In 2016, Gerald Tenenbaum drastically generalized this estimate. So if we let sk of x be the sum of 1 over the product p1 through pk, and this is overall ordered k tuples of primes p1 through pk whose product is less than or equal to x. So he proved that this is a degree k monic polynomial in double log x plus an error term that tends to 0. And moreover, he gave explicit formulas for the constants in the polynomial. So these are the coefficients. So it's this big formula here. And these are multinomial coefficients. And B is Merten's constant. Gamma is the Euler constant. And then the capital gamma is the Euler gamma function. And this is the mth derivative here in the superscript. So that's just summarizing what all the things are in this big formula. Tenenbaum's proof follows the Selberg-Delange method from complex analysis. And he starts by using Perron's formula to represent sk of x as an integral over the vertical line with real part c in the complex plane. So c is some positive constant here. And the integral is of the kth power of the prime zeta function of s plus 1. So this again comes from Perron's formula. So the prime zeta function is like the zeta function, but the sum is restricted to reciprocal s powers of prime numbers. And again, the sum in Tenenbaum's theorem is overall ordered k tuples of primes, p1 through pk, well, up to x, with the product up to x, that is. And some terms occur multiple times. So for instance, if we look at the case where k equals 3, 1/30th occurs 6 times. For instance, it's 2 times 3 times 5, and it's also 2 times 5 times 3, and so on. On the other hand, 1/12 occurs 3 times. 2 times 2 times 3, 2 times 3 times 2, and so on. And then 1/8 occurs only once, because we could only represent it as 2 times 2 times 2. So we wanted to find a generalization where each term is counted once and only once. And the big omega function counts a number's prime factors with multiplicity. So it's the number of prime factors of a number n. And repeated prime factors are counted according to their highest power. And we call a number n a k almost prime number if big omega of n equals k. So we're studying the sum Rk of x, and this is the sum of reciprocals of k almost primes less than or equal to x. And this differs from Papa and Tenenbaum's sum because each term occurs once and only once. So for each k almost prime n. And here's an improvement, which is substantially more refined from last year's talk. So for any integer n, at least 0, there are constants alpha j, such that R2 of f
I think we can't hear you anymore.
I was able to hear the whole time, so I don't know.
Oh, okay, I'm sorry. Must be me.
Is that coming through okay?
Oh, I can hear you fine now. Okay.
Okay. And then we have these smaller order terms. So it's 1 over log x to the j times a constant, and then plus an error term that's big O of 1 over log x to the n plus 1. And then the implied constant depends on n. And here are the formulas for the alpha j. And the integral here involves the error term in Merten's original theorems. That's what E of t is. And we found a nicer formula for the alpha j's as well. So if we look at the limit of the difference between the sum over p up to x of log p to the j over p and log x to the j over j, and then divide by j. So that limit is known to exist for all j, and that's actually equal to alpha j. So it gives a nicer representation of these constants. In particular, alpha 1 is the constant appearing in a strong form of Merten's first theorem. So that's the limit of the difference between log x and the sum up to x of log p over p. So this is a well-known constant. It's about 1.332582. And this is in a strong form of Merten's first theorem. And the fact that this limit exists is actually equivalent to the prime number theorem. So that was interesting to see the this expression from Merten's first theorem pop up. So we have nearly completed a proof for the general case of k. So Rk of x is a degree k polynomial in double log x. And then it can be shifted, so it's double log x plus b, plus an error term that tends to 0. And here's a formula for the polynomials. So we have an expression similar to Tenenbaum's theorem, but it also involves combinations here with the prime zeta function depending on the multiplicity of the prime factors. And this first sum is kind of a big index. It's over all partitions of k. So for example, if we look at the 9 almost prime of the form p cubed q cubed r squared t, n3 is the number of primes with exponent 3, so that's equal to 2 here. And then n2 and n are both equal to 1. And we could also call n sub 1, but it plays such a different role that we just call it n here to distinguish it. So recalling our notation, so EK is an error term that tends to 0, and L is double log X. Here are the formulas for the first few K values. So again, this is like Tenenbaum's sum, but it accounts for the fact that we're counting each K almost prime once and only once, so there's an inclusion-exclusion argument. And the terms become more complicated as K increases. So we've proved now that the formulas hold for all K up to the numerical value of the constant coefficient, which isn't quote unquote seen by the current method. And let's look at that. So the heuristic is to combine Tenenbaum's theorem with a theorem of Lichtmann for almost prime zeta functions. So if we let pk of S be the sum of reciprocal S powers of K almost primes up to X. And note that P1 of S is just the prime zeta function because one almost primes are just prime numbers. And Lichtmann derived a combinatorial formula for the almost prime zeta functions. And the terms here are multimonomial numbers of integer partitions. So there's a general formula. And so unlike these convergent sums in the K almost prime zeta functions where S is bigger than 1, our K of X is divergent. So it goes to infinity with X. And unfortunately, that means that the formal power series identities that were used for the combinatorial formula for the almost prime zeta functions can't be used directly here. Yet one might expect the following. And let's look at R3 of X, for instance. So we want each 3 almost prime up to X to be counted once and only once. So we're dividing by 3 factorial, so it'd have to occur 6 times in the parentheses. So if PQ and R are distinct, PQR occurs 6 times in the first sum and no times in the second or third sum. For a prime of the, 3 almost prime of the form P squared Q, where P and Q are distinct, it occurs 3 times in the first sum and then 3 times in the second sum, thanks to the 3 out in front. And then for an almost prime of the form P cubed, it occurs once, 3 times, and 2 times, which is 6. So for small k, we can use this inclusion-exclusion argument directly. And so to prove the general formula, we use partial summation with the counting function of K almost primes. And the Sath-Selberg theorem gives a very nice expression for this. So the number of K almost primes up to X is X over log X times a degree K polynomial, or sorry, K minus 1 polynomial in double log X, plus an error term that tends to 0. And this is actually uniform for all X at least 3 and all K up to 1.99 double log X. And in fact, it's 2 minus epsilon times double log X. And here are the coefficients of QK, the polynomial here. And they're given in terms of the derivatives of nu at 0. So nu is this function here. And it involves the gamma function and an infinite product extended over all primes. So this actually comes from the realization that nk of x is the coefficient of z to the k in the sum of z to the big omega of n and up to x. So it's an Euler product. So partial summation together with the Sath-Selberg theorem gives a formula that is fairly immediate for Rk of x. But unfortunately, it doesn't tell us anything significant about the constant coefficient. And it takes some work to show that it's equivalent to the combinatorial formula that we had earlier. But the expansions do agree by a careful manipulation of terms. assuming that dk of x is what it's supposed to be, so that it would fit the same pattern here. It's the kth derivative of nu at 0 over k factorial. So here's nu again. And if we expand it using the Weierstrass product formula for gamma, we actually get the exponential of a Taylor series. And here the C1 is Mertens constant, and then the rest of the CJs and the coefficients here involve the prime zeta and the zeta function at j. And for short, let's let nu j be the jth derivative of nu at 0 over j factorial. So these are the coefficients. And so the remaining hurdle is to show that dk is equal to nu k, so that we'd have this nice expression for rk of x that works, including that constant coefficient. And we also have a recurrence relation for nu k. So that's given here. So it's 1/k times the sum from j equals 1 to k of cj times nu k minus j. And just a reminder, so cj is this expression from the previous slide involving the prime zeta and the zeta function at j, except c1, which is Mertens constant. So this recurrence relation allows us to readily compute numerical values to many decimal places for nu k. And we use peri-GP, and Mathematica can also be used. And so here are the numerical computations, and we're actually comparing nu k to 2 to the negative k power, and we observe the following pattern. So if we look at the ratio, so this is nu k times 2 to the k. It appears that it's approaching a limit, so it's about 0.18934. And we were able to prove that if nu k does have an expansion of this type, then it's given by the following formula. And it's found by looking at the residue of the pole of nu at z equals 2. And you can see this comes out very, very close to what the data suggests. And so what remains here is to prove existence of the expansion. Because if it exists, it has to be this form. So thank you very much. And I'm happy to talk about any questions that people have in the remaining time.
Thank you very much.